This is an artist rendering of what a first human mission to a near-Earth object could look like in the mid-20s. We could actually go to the kind of objects that we think are made of the building chemical blocks that could have helped seed life on planets. There are a class of these small objects called near-Earth objects that are, we think, made of carbonaceous materials. Those things certainly collided with early Earth and early Mars. Now, the interesting thing about this is we don't know enough to design this mission now, so there are artists and engineers have come up with what we'd like to do. But since we haven't characterized these objects, except for the one, we don't know what we would do. But one of the things we feel we would have to do is we wouldn't go land, because there's no landing on an object that you bounce off of. I mean, it'd kind of be hopeless, almost futile. So what we would do is send people down on rope chains, and they would go and tether themselves to the surface. It's kind of like climbing the wall of a rock, you know, in the Grand Canyon, but knowing that if you fall off, you're going to float away. I mean, a little less risky, but you wouldn't want to float away in free space. So here you see a couple of women tethered to a piece of an asteroid. Again, we don't know that they look like this. So one of the things you're going to see in the next decade is missions to asteroids by robots to see what they're really like. Sampling them, understanding how to operate around them, it's a very important step. So you can see the last, here's a woman and a guy coming off on their tethered thing, flying back, little rocket packs, back to the mothership to come home. So this is an artist rendering of what might happen. Some of you could be in the position of helping to make these kind of missions happen. So I want to remind you before I go to Mars that we actually have a constellation of 14 satellites in Earth orbit. And you might say, well, what's NASA doing for global warming, for climate change? We are doing a lot. Very often the things you see on the Weather Channel every now and then, what's the weather like today? It's going to rain again, sorry. Or the Snowmageddon we had this last winter here, great fun, by the way, is informed by these satellites. We actually can produce a global mosaic of the entire Earth's surface every day from the Terra spacecraft. We study the winds. We have exploratory missions. We study the nature of how the oceans work. This is part of what we do here at NASA Goddard. We do it in partnership with other centers like JPL. So the Earth is a planet. Why should we neglect it? And by watching how it moves and changes, particularly its atmosphere, oceans, and land cover, very quickly, we get a little impression of how our own planet works. Now, one thing NASA's done in the last couple of years, probably none of you heard about, but I have to feel that I talk about it. We've actually mapped the polar ice sheets in exquisite detail. This is a flyover rendered completely by computer of the calibrated Landsat mosaic of Antarctica. It's a fingerprint for the state of ground-covered ice for our planet. If that changes too much, that tells us something. We've watched over the last 20 years the retreat of not only mountain glaciers, but of the ice sheet in Antarctica. Pieces the size of Delaware have broken off. This is a concern of ours, because the runaway rate of these changes may be normal, but we haven't experienced them as humans who are aware of it ever in our history. You know, in the Middle Ages, I think people probably weren't aware of anything. But now they are. We are a living planet. We talk, we breathe. And when you see recessions of the ground lines of ice that are so rapid, we get worried. The other thing we're able to do is take stock of the biological health of our planet in 2D. This map of the ocean color and related quantities allows us to see the state of health of biomass growing in the ocean. And these big dark purple and blue zones are areas where there are less living things. And we can do these kind of mappings from missions like CWIFS, from our MODIS, routinely. You can see blooms of high biological production in the oceans, of course the greens on land, and the deserts. One of the things NASA wants to do in the next decade is do this in 3D. What's the biomass of the forests? How is the carbon system changing? This is critical. And so we have mission plans to do that. So the Earth is a planet. It's a living planet, the only one we know. We're looking for Earths. So here's Earth in the living planet stage. And this is what we do in our Earth Science program, again, superimposed on that. So what about Mars? Everyone asks me, was Mars ever like this? Is Mars truly the astrobiological planet that we all know and love? Well, for the last 15 years, all of you who have cared to notice have witnessed the greatest robotic era of exploration of the planet Mars in the history of women and men. We are at a time of every time we go, it's a new revolution in how we see the planet. This fly around I'm showing you now was something I dreamt about when I first came to NASA now 25 years ago. This is Mars in 3D. The hot colors are high, the other colors are low. This is the South Polar Ice Sheet. We now know it's made of water ice. Before this mission, the Mars Global Surveyor, we thought it was all frozen carbon dioxide, dry ice. It's water. Sorry about that, folks. This is the North Polar ice sheet, the great hockey puck. Not a puck, really, but it's a large ice sheet like Greenland on Earth. I don't know if any of you have ever been to Greenland, but if you've flown over it, this is about the same size. Spiraling canyons. The Mars atmosphere exchanges itself with the surface. 25% of the atmosphere freezes out and then sublimes into the atmosphere every single year on the planet Mars. The mass balance of the polar ice sheets, predominantly made of water ice, are a critical barometer of climate history on Mars. We think Mars has gone through monumental climate sweeps, partly because its rotational axis, the angle axis of obliquity, as some of you may know, actually doesn't wobble a couple degrees like Earth's, which causes huge climate changes over scales of 10,000 to 100,000 years. On Mars, it wobbles by 20 to 30 degrees. So imagine if the Earth's axis, went like, well, we would have a different climate state. Trust me. Physics does not lie. People try to legislate it, can't change it. So Mars has gone through wild climate change. And we now know that by measuring things about the planet, both in 3D and in the atmosphere. So we did this mapping here at Goddard with our partners at JPL as part of the Mars Global Surveyor mission. We now know any place we want on Mars, good to about a foot or two. That allowed us to send missions to Mars that before this mapping, and before we got to look at the biggest volcano in the solar system in 3D, would not have been possible. I'd like to show this picture for a minute. This is Olympus Mons. It is 6 million cubic kilometers of rock. It has around it a large cliff line, an escarpment, that is 3 to 4 kilometers high. When we first saw that in photographs in 1972, people said, oh, geez, I didn't realize that would happen. Wonder why? And they did a few calculations. They realized big giant volcanoes are too heavy to hold themselves up, and they collapse. Some people decided, well, why don't we see that on Earth? I wonder why. Let's go look. We looked all around the big volcanoes of Hawaii. They all have big flank collapses like that, only they're underwater. Never saw them. What happens if a whole side of a volcano, like all this part, collapses? On Earth, it moves stuff. If it's underwater, what's it going to move? Water. What's the water going to do? It's going to turn into gigantic tsunamis. Gigantic tsunamis that could actually affect the coastlines of the Pacific in the United States, in the east from other places. So we discovered by looking at Mars how some aspects of our own planet work by just observing them. So this is one of the discoveries where planets informed our own history. On Mars, we have a system of giant volcanoes. We also have Mars seen now here, where we've taken topography and imaging from one of our satellites, Odyssey, and put it together. We do have little mini tornadoes on Mars all the time. And what we also have on Mars, which is so staggering, aside from impact craters, is the solar system's largest canyon system. You might say, well, how did little old Mars, 38% the size of the Earth, okay, not big enough to have worked the way the Earth did, produce a canyon system here that makes our own Grand Canyon dwarf in comparison? How did it do that? Why does Mars work so different? Here's Los Angeles for scale. You can see 7.2 kilometers. Our Grand Canyon, I'll show you in a minute, would fit in one of these little spare canyons. And if any of you have been down in the canyon on a mule, I think you'll know, that was a joke. The mules are a little bit nasty at times, but they are fun, actually. So this is a canyon system that goes 3,000 kilometers across the midriff of Mars. Why is that? What ripped apart this planet with a crust and possibly with a water history unlike anything on Earth? That's one of our conundrums, one of our enigmas. So here we are flying up one of those canyons seen from Odyssey and our Mars Global Surveyor. The Grand Canyon for scale would fit right here. So if any of you have been there, it's pretty big, pretty dog. You don't want to fall in. They do lose a few every year, I've been told. But so one of the things we learned about Mars then, the scales of things that operate on Mars, climate, are different. So in 2003, we launched a pair of twin rovers,